Welcome back to the Machine Design Engineer YouTube channel. In today's video, we are going to select a servo motor from manufacturer's catalog. Selecting the right size servo motor is one of the most critical steps in machine design. An undersized motor can lead a overload and poor performance, while an oversized servo motor increases cost and reduces system efficiency. In this video, we will learn how to select a correct size servo motor from real manufacturer's catalog using real engineering calculations, not any assumptions. We will verify speed, continuous torque, peak torque, RMS torque, inertia ratio, and finally select a correct size servo motor from manufacturer's catalog. For our laser cutting machine Z-axis, every high performance CNC machines like laser cutting machines and automation system depends on one most critical component, which is servo motor. But selecting a correct size servo motor isn't as simple as choosing a power rating. It requires a complete engineering analysis. Speed, force, torque, inertia, RMS torque, and peak torque. In the previous chapter, we completed every calculations required for servo sizing using a real machine data. Now it's time to compare our calculated values with the manufacturer's catalog and select a correct size servo motor using a same process followed by industrial application engineers and design engineers. Let's begin a servo motor selection from manufacturer's catalog. Let's get a quick recap for previously calculated values. We have moving mass 15 kg. Our selected ball screw is 1610 ball screw, means 16 mm dia and 10 mm lead. Our ball screw length is 288 mm. Ball screw mass is 0.517 kg. Ball screw efficiency, we are considering a 90% efficiency, and this efficiency we have taken from a manufacturer's catalog. Maximum speed is 300 mm per second. Acceleration time is 0.3 second. This acceleration time is 0.3 second. Constant speed is also a 0.3 second. Our cycle time is 1 second. Friction force, which is 0.1 Newton, we have considered. Coupling inertia, which is 4.5 multiplied by 10 raised to minus 6 kg meter square. This value is also taken from manufacturer's catalog. Our required motor speed is 1800 rpm. We have calculated in a previous video. Our calculated motor speed, our lead is 10 mm and our linear travel is 300 mm per second. So our motor speed is 300 multiplied by 60 divided by 10, which is 1800 rpm. So we get a required speed 1800 rpm. Next step is linear acceleration. So our linear travel is 300 mm per second and our time is 0.3 second. So we get acceleration 300 divided by 0.3. So we get 1000 mm per second square, means 1 meter per second square. Next step is acceleration force. We know the formula F is equal to ma. Our total moving mass is 15 kg and our acceleration is 1 meter per second square. So we get an acceleration force 15 Newton. Gravity force means total weight multiplied by gravity, and the gravity value is 9.81. So 15 multiplied by 9.81, we get 147.15 Newton. So our total linear force is gravity force plus acceleration force plus frictional force. Gravity force is 147.15 plus our acceleration force is 15 Newton plus frictional force. We are considering frictional force is 0.1 Newton. So we get a total linear force 162.25 Newton. Next, required screw torque. We know the formula torque is equal to force multiplied by L means lead divided by 2 pi n. We are considering 90% efficiency. First convert lead into a meter. Our lead is 10 mm. After convert into a meters, so we get a 0.01 meter. Substitute the values in the formula. 162.25 multiplied by 0.01 divided by 2 pi multiplied by efficiency. We are considering 90% efficiency, so multiply 0.9. So we get a torque 0.287 Newton meter. This is our continuous required torque, which is 0.287 Newton meter. Next step is to calculate load inertia. We know the formula JL is equal to ML divided by 2 pi bracket square. Substitute the values in the formula. Our total moving mass is 15 multiplied by 0.01, which is our lead, and divided by 2 pi bracket square. So we get a load inertia 3.80 multiplied by 10 raised to minus 5 kg meter square. Next is wall screw inertia, which we have calculated in a previous video, and the value is 1.65 multiplied by 10 raised to minus 5 kg meter square. Next is coupling inertia, which we have selected in the previous video from manufacturer's catalog, and our selected value is 4.5 multiplied by 10 raised to minus 6 kg meter square. Next is total load inertia, which we have calculated in previous video, which is load inertia plus ball screw inertia plus coupling inertia, and our total load inertia is 5.90 multiplied by 10 raised to minus 5 kg meter square. Next is motor rotor inertia, which is selected from manufacturer's catalog. We are referring Panasonic catalog, and by using a Panasonic catalog, we get a rotor inertia 0.58 multiplied by 10 raised to minus 4, means 5.8 multiplied by 10 raised to minus 5 kg meter square. And to calculate inertia ratio, we need to divide a total inertia by motor inertia. Our total inertia is 5.90 multiplied by 10 raised to minus 5 divided by 5.80 multiplied by 10 raised to minus 5. So we get a ratio 1.02. As per Panasonic catalog, the maximum limit is 30:1. Our calculated ratio is 1.02 as to 1. This is an almost ideal inertia match. Next is angular acceleration, which is denoted by omega. Our motor speed is 1800 rpm. Convert into a radian per second. So we know the formula. Omega is equal to 2 pi n divided by 60. Our n means our motor rpm is 1800 rpm. Substitute the values in the formula. 2 pi multiplied by 1800 divided by 60. So we get 188.5 radian per second. Our acceleration time is 0.3 second. To calculate angular acceleration, divide omega by time. Our omega is 188.5 divided by 0.3. So we get 628 radian per second square. After calculating angular acceleration, next step is to calculate acceleration torque. And to calculate acceleration torque, we know the formula total torque multiplied by angular acceleration. Substitute the values in the formula. We know our total torque is 5.90 multiplied by 10 raised to minus 5, and our angular acceleration is 628. So our total acceleration torque is 0.037 Newton meter. After calculating acceleration torque, next step is to calculate peak torque. And to calculate peak torque, we know the formula: torque required to rotate the screw, or torque required to overcome the gravity, plus acceleration torque. So we have calculated a torque required to rotate the screw, which is 0.287 Newton meter. So we get a peak torque 0.324 Newton meter. After calculating a peak torque, next step is to calculate RMS torque using a motion cycle. Acceleration 0.324 Newton meter for 0.3 second. Our constant speed is 0.287 Newton meter for 0.3 second. This acceleration is 0.250 Newton meter because gravity minus acceleration for 0.3 second. Remaining dwell is 0 Newton meter for 0.1 second. To calculate RMS torque, we know the formula. Substitute the values in the formula, so we get RMS torque 0.298 Newton meter. After calculating all required values required for servo motor sizing, now next step is to select a servo motor from manufacturer's catalog. We are selecting a Panasonic manufacturer and we are using a Panasonic catalog for motor selection for our servo sizing and for our fiber laser metal cutting machine Z-axis. You can download a Panasonic servo motor selection catalog from description and also download a motor selection step-by-step guide and compare all our calculated values with catalog and this motor selection guide, so you can understand how a correct servo motor we have selected. Step 1, identify motor model. We are selecting a MIMS A6 servo motor family, and series we have selected MHMF series. Motor type is high inertia. Connector type protection class IP67. Flange size 60 mm square, means 60 by 60. Motor type rotating AC servo motor. Step 2 is check power and voltage. We are selecting a 400 watt servo motor. Step 3 is check torque specification. With MHMF series servo motor, we get a rated torque 1.27 Newton meter. Continuous stall torque is 1.14 Newton meter, and momentary maximum peak torque means peak torque 4.46 Newton meter. And as per our calculations, our continuous torque requirement is 0.287 Newton meter and rated torque requirement is 1.27 Newton meter. And as per our calculations, our peak torque requirement is 0.324 Newton meter, which is less than 4.46 Newton meter. So motor satisfy our torque requirements. So next step is check speed specification. Motor rated speed is 3000 rpm and motor maximum rotational speed is 6500 rpm. So our required speed is 1800 rpm and motor rated speed is 3000 rpm. So our required speed, which is 1800 rpm, is less than 3000 rpm. So motor satisfy our speed requirements. Next step is check inertia. and inertia ratio. And motor rotary inertia is, as per Catalogue, 0.58 into 10 raised to minus 4 kg meter square. Recommended inertia ratio is 30 times or less than 30 times. Our calculated inertia ratio is 1.02 as to 1, which is less than 30. So motor satisfies our inertia and inertia ratio requirements. Next step is to check encoder specification. Motor is compatible with 23-bit absolute and incremental encoder. We are selecting a 23-bit absolute encoder. Next step is to check brake specification. And MINAS A6 servo motor family and MHMF series comes with brake and without brake. We are selecting a motor with brake. So next step is check permissible load. So you can see our motor is past our permissible load requirements. Next step is to check torque characteristics graph, and our motor is comfortably operate within continuous run range for continuous duty. Next step is to check dimension. The flange size is 60 by 60 mm and motor output shaft is 14 mm. And final selection summary is this motor is fully satisfies our all calculated requirements and is suitable for our fiber laser cutting machine Z-axis. So this is how we select a correct size servo motor systematically from manufacturer's catalog, not just based on power, but by checking continuous torque, peak torque, RMS torque, inertia ratio, encoder, and permissible load. In this example, we verified our calculated requirements with manufacturer's specifications and completed a servo motor selection for our fiber laser cutting machine Z-axis. Remember, a correct servo motor selection is not about selecting a bigger motor, it is about selecting a right motor. If you found this video useful, like the video, subscribe the Machine Design Engineer YouTube channel and press the notification bell. Thanks for watching. I will see you in the next video.